Okay, tell me what's happening now, because I think I know what it was, and I think I have it solved. Good morning, everybody. It's 11:59. Okay. I think what's happened here is that I had something yesterday that was recording what I was playing through the computer, and it's probably repeating now. Yes, we're all better. Okay, I'm going to start again then. Undo everything. Undo everything. Good morning, everybody. It's 11:59, 5 minutes later. All right, so so what I want to do is I'll just put this back the way it was. There we go. I want to pre-fill these values, and if we change something in it, I want that recorded. So if the page is reloaded, then it will remember what we've just done. Thank goodness it's over. Yes. Right. So what I'm going to do here is all the bits that say value, I'm going to change them to data value. And that means it's kind of attached to it, but it's just data. It doesn't do anything. It doesn't actually set the value. So I'm going to swap value equals into data value equals. The program I'm using here is called Vim. It's well worth learning, but it's a very steep learning curve. Now I recommend you learn it, but I'm not gonna push it because people are scared of it. All right. So I've got all these values here. Now, if I reload this page, you'll see everything's empty. So what we want to do is, before we run init, we want to set the values from the data value or from local storage. Now, local storage is a way to record information into your computer in kind of a temporary memory that it records into your computer. But if you were to clear all your caches and stuff like that, or if you were to go to a different computer and load the page, that's not there anymore because it's different. It gets cleared. It's a different computer. So what we're going to do here is, for every input, so I'm grabbing all the inputs, we're going to do an each on it. And we'll say that the input equals this. This, in this case, is we're looping through each input. That's an input there, that's an input there. So that corresponds to these objects here. And we're going to go through them, and for each of them, we're going to create a variable called imp, and then we're going to set the value of that, imp.val. Now, I'll start off by saying this, imp.data value. Now, what that does is it pulls the information from the data value of the input of what we created there, and it will put it in there. So if I run that now, we should have ended up. Do you know what I need is a console with errors in it. And I don't see any errors. Okay. Now, so data val imp.data value. And I'm going to do a console log just so we can see what actually is supposed to be happening here. So imp and imp.data value. So that should give us a list of the objects that are being none. Okay. Oh, I'm putting it in the wrong place. How silly is that? There. I'll put that in there. Yay. Okay. So what happened there? What's happening here is that this little snippet of code is looking through every one of these objects, and I'll just inspect one of them. And it's grabbing the value, the data value, and it's turning it into a real value of the input. So it's not, a data value is kind of metadata. It's data that's attached to it, but it doesn't actually do anything. I'm learning C++. That's good. It's not what I'm teaching, but very good. C plus? Does C plus plus? I think you mean C sharp. Okay. Right, so right, so what we want here is that now if the input is changed, then we want to record that into local storage and use that instead. So let's create a new thing here. Where is this starting? Init, run movements, restart. Right, when I set up this originally, we used this little onload thing here. Now, that's not the best way of actually starting off a little piece of script. Because we're using jQuery, we can actually do something a little bit funkier. Inside the script, we can do this. Now, I know that looks a bit weird. Let's make that a bit easier. We'll do it again. Right. So that's basically a way of telling jQuery, run this piece of code when the page loads. Now, so when the page is loaded, we want to do this this thing here that I did here. But we also want to attach events to the inputs, so that when C sharp, not C plus, yep. So when the input changes, we want to record the change. So let's do that. Imp.change. Don't even need this. We can do this instead. So when the imp is changed, we can set local storage for this input. Now, if we just go back up to the inputs and have a look at how they're generated, you'll see each input has an ID. So I'm going to record the information against the IDs. So we'll say that local storage imp.attribute ID equals imp.val. Let's have a look and see what that does. Alright, so I'll go into console here and clear it out. I'll just get rid of this other console log so it's not needed anymore. And reload this page. I think I broke something there. Oh yeah, I forgot to actually call init then after that. Right. Okay. So if we have a look at local storage, you'll see it's empty. There's nothing in it. But let's make a change to something. Let's change this to 15. And then look again. Right. So now what's happened is that I've killed everyone. Now what's happened is the input here changed. And then when it changed, this piece of code ran. So we record into local storage based on the ID of the input. We set it to that value. So we'll say that local storage inf_or is equal to 15. So that's infection radius 15. We're setting it to 15. Now, if I reload the page, it goes back to 5. That's because we haven't told it yet how to use that local storage. So well, let's do that. So in this bit here, the input value where we're setting it to the data value, let's check and see if local storage has a value. And if it does, we'll use that instead. Now, so we'll see, I'm going to do this the longhand way. So var val equals local storage imp dot attribute ID. Now if I'll just show you what that looks like for now. So console.log. Do you know what? This imp attribute ID, I've written that twice now and it's ugly. So let's just make a shorthand version of that so I don't have to do it again. Var ID equals, okay, and then I can replace these with ID. And that makes things easier to read. Okay. Alright, so we've got ID, and there's the val. Now, let's have a look and see what is ID and what is val when I reload the page. Clear this first, reload. Density, undefined, init, inf, undefined, inf or 15, because we set that. Immune chance, undefined, blah, blah, blah. So these are all the different inputs that we have here, and these are the values that are stored. So if the value is equal to, in fact, if it's identical to undefined, there's a difference between equals and identical to, okay? Let's see, something like that is equal to 1, but that is not identical to 1, okay? They're not the same. It's like an Irish person and an Irish person may be equal because they're both Irish, but they're not identical. They're not the same person, okay? So in this case, the string 1 is not identical with the number 1. They're not exactly the same. They're not the same thing. So if val is identical to undefined, now undefined is a special value in this. If val is identical to undefined, well then we want to set it to imp data value. Okay, and then we're going to set the input value to what we figured out we actually want val to be. This should work. So infection radius here, I'm expecting that to be 15 when I reload. There we go, 15. Yay, genocide. Okay. So if I change that, that's a bit scary. Let's say I change that back to 10. All I've done is change it. I haven't clicked save or anything like that. I just changed it to 10, reload the page, and you see it sticks at 10. Now that happens with all of the inputs that we have here, because this wasn't special. I wasn't saying input radius, whatever. I said all inputs. If any input changes, record its value. So let's try changing the initial infection size to 5 and reload. 1, 2, 3, 4, and I guess 5 was around here as well. 1, 2, 3, 4, 5. Okay, so now what we can do is we can just reload the page each time, and we have the same settings as before. So if you make some settings and you like them, you now still have them. And this even happens if I close the browser down and restart it. You still have the old settings. Now, there's a way of clearing it using JavaScript. If we just go in here and we'll just say local storage equals dot clear, I think it is, local storage dot clear. Yeah. Okay. And now if I reload, you'll see we're back to normal, to the undefined for everything. Okay, so if you really want to clear everything. So 1 is identical to 1. Yes, 1 is identical to 1. Now, okay. Right. In JavaScript, we have this interesting thing where strings and numbers and things are immutable. Immutable means that they do not change. So if I say var a is equal to test and var b is equal to test. Now, you might think that a is not identical to b because they're different variables, but in fact the strings themselves are identical. And it's a strange reason, but it's basically a memory saving thing. You see, if you record something let's say 3 megabytes in size, and you make another one which is 3 megabytes in size, and it's the exact same string, you're wasting memory if you have both of these in the computer's memory. So instead, what happens is the variable is actually pointing to the memory, and Amit was there talking about C#. Now in C and C++, you have memory. When you're creating something, you allocate memory. And this is basically what happens here, is that you're actually allocating a space in memory, and the strings and things are recorded into those spaces. It's like saying, it's like it's in a box. And you're saying, what is A? A is the contents of that box. B is the contents of that box. Well, they're both identical because they're both pointing at the same box. Okay. So we're now recording things. So we can actually record things. Now, let's just make this pandemic a little bit deadly so we can see what happens when we make a hospital. Right, so let's say immunity chance, infection radius. Let's say we increase the infection radius to 6. See what that looks like. Doesn't look like much. Okay, let's increase that again to 7. Okay, so we've got something going on there now. Right, now I expect that will get deadly very, very soon. Right, so what is a hospital? What is a hospital? When we're talking about pandemics, what is a hospital? Well, a hospital, that's a print finished. A hospital is an area where you put sick people. Simple as that. Now, in a pandemic, what that means is you're taking the infectious people out of where they are, and you're putting them all basically together in the same place, where they might infect each other, but they're already infected, so that's not really going to do any harm. So they're all in the same place, but they're away from the uninfected people. Now, we also need to have a boundary between the hospital and everyone else. So in this case, like in reality, the boundary would be the doors of the building. So people are not allowed in through the doors, or not allowed to walk out through the car park. So we need to define something like that. So we need to have a function which defines, well, a few functions. One of them is going to define, are you allowed to move to this place? So we can see that people in this are moving, and they're like, when they hit against the sides, they kind of bounce back. But there's nothing beyond that. It's like they're free to move wherever they want. But we need to have some places where people are not allowed to be. So they, if movement moves them into that place, well, they're not allowed to go there. They have to move somewhere else. They have to, or maybe they're just not allowed to move. So let's define that. We're going to create a function saying can move to. All right, can move to, and it's just going to have you just give it parameters like x and y, and it will return yes or no. Yes is true and no is false. So we'll create a function called that. Function can move to x, y. You give it x and y. We'll start off by just saying yes, you can move wherever you want. Okay, so let's go back into the functions. There's one there called run movements. Now, we have all this stuff here where we're basically doing weird stuff here, like saying if you go less than 0, well then you just do all bouncing against the walls and all that. Now, I'm going to move all that into can move to. So we really want to have one place where you're saying, can you move it to this or can you move it to that? If you could define can move to in multiple areas, can make walls or roads, we can make walls. Roads are not really the same thing. Not really the same thing. There's a way that you could say they're similar, in which case you're saying, all right, a road is a simple way to move from A to B. Okay, now if you think of, let's say in a town, you might have your house and somebody else's house. And if you go straight from your house to another house, there's nothing stopping you from doing that, but there are obstacles. Like you might have to climb over a wall, or you might have to go through somebody's house. Those are obstacles, but they're not stopping you. So you could think of that as kind of a tacky way of getting from A to B. Or in computational terms, you might think of that as an expensive way of going from A to B. So you would basically measure A to B not just as distance, but as a number which includes distance and includes the various difficulties along the way. Now you could say that a road is a way that has a very low expense to go from A to B. So in that case, getting from here to here, in purely distance terms, a straight line is the quickest route. But if a straight line includes expenses such as climbing a wall or going through a house, well then you could add numbers onto that, in which case the quickest route might actually be go here, then here, then here, in which case the roads have very little expense, which means that the expense of traveling from here to here is less if you just go in a kind of a circuitous way, which involves the roads. That's how we figure out the way route planning, basically route planning from here to here. You measure the expense of going from here to here. It's not just distance. Okay, so yes, you could say that roads and walls and all that are can move too, but in that case you're not saying true or false. In that case you're returning the expense, and yeah, the expense basically of moving from A to B. So let's move this stuff down into here. Okay. PX minus. Right. So if can move to, I think there was a mistake in the old version. No, oh yeah, that was before. Right, yeah. Okay. Let's see, we're gonna add in new x, new y. We're gonna create these, which will be p.x plus, you can see where I'm going here, new y is equal to p.y plus that. Okay. So now instead of just setting these, we're going to check and see, is that allowed? Right. So if can move to new x, new y, then we're going to set these values. p.x is equal to new x, p.y is equal to new y. Okay. Now, don't need this anymore. Let's move these down to there. Okay. Now, I'm going to rewrite these. Yeah. No. Yep. So, if new x is less than 0, well then we're just going to return false. No, you can't go there. No. Simple. We'll just keep it nice and simple. No, you can't go there. If new y is less than 0, return false. Now we could get fancy and do the same as we did last time, but that's too fancy. If new x is greater than or equal to SW, you can see I'm basically copying the ifs that we had down here. Return false. And if new y is greater than or equal to SH, return false. Otherwise, return true. Okay, so you can see what we're doing is we're measuring how far you're traveling. We're seeing like, is it okay to go there? We set a new x and new y. We see, is it okay to go there? And if so, you set the values. Now, this should still work. Should. I broke it. Okay. New x is not defined. Oh, well, that was silly. There we go. It's because they're actually called x and y in this function, where I called them with new x and new y here. So, what is this? What OS are you using where the terminal's called Terminator? It's actually something that you can download. See, the handy thing about Terminator is I can do things like that. I can split things. You know, it's really fancy terminals. It's nice. Just download it. You'll find it somewhere. I'm running a Linux distro, but the terminal is just terminal. Yeah, the default terminal for most operating systems is pretty simple. I just like this one. I install it on every operating system I use, which is always Linux. I think it's Linux. Yes, it is. I'm using Fedora Linux. Okay, so let's check this. Yeah, it's working again now, and we still have things moving around. Yay! So we've got things moving. Now we're getting places. Now we can define things like a hospital. So I'm going to define basically a wall. So let's say we say the top left 50 or so, or 100 by 100 square is going to be the hospital. So we're going to have a kind of an artificial wall of, let's say, 10 pixels around that where nobody can go. Okay? Alright, so we'll do that. Now, so it's pretty simple to do. So if x is greater than, let's say, greater than and equal, what did I say, 100? And x is less than, and I want it to be, let's say, 10 wide, less than 10 wide, then return, oops, it's kind of complex. All right, and y is less than 110. Yes. All right. So I'm basically defining a rectangle like that, and I'm saying no, you can't be in that rectangle. Yeah. We'll have another one. If x is if y is greater than or equal to 100, and y is less than 110, and x, again rectangle, is less than 110, return false. Now, why do I have these bits at the end? Okay, if I don't have these bits at the end, well then we have a rectangle that reaches from here all the way down to the bottom. But we actually we want to allow movement here. We want to allow movement here. We just don't want to allow movement here or here. Now, this is still not ideal. I mean, I'm kind of predicting what the computer is going to do here. I predict that we're going to have a lot of dots here and here that just will stop moving. Okay, reload. Now, where's 100? Did I even measure it right? Where is 100? I don't know what I just did. Alright, let's try this again. If x is great, I'm going to reduce this down like that. So I'm making the rectangles bigger. Well, there we go. Ah, that's where it was. Right. There's no numbers here, so I'm just kind of guessing everything. Is anyone apart from me getting lag issues? Yes, I am. Alright. So let's say I increase this again. Right, so we'll increase this back up to, let's say, 90, no, 100. 100. And I'm just going to have this 20 wide instead of 10. Now, so if I reload this, you'll see that we have no movement here. Okay, so these people are basically stuck on a wall. But what that also means is that these people are not going to infect these people. All right, so let's stop people from even generating there in the first place. We don't want people to be stuck in the wall. Can people in the simulation walk through each other? Yes. The small people. Okay, let's see. So we want, that's in initialize, so set up the population. Now, I'm going to do a little bit of fanciness here. So you can see here, math.random, this is where we're initializing the position of a person. Now, I want to basically do this over and over and over until, like, they're randomly choosing a position. So in this case, they're randomly choosing to be in the middle of a wall. But I want them to just keep trying until they find a valid place to be. So we're going to do that with a do loop. So do. While can move to. Can move to is basically checking, is this a valid position to be in? P.x, P.y. While not can do. Alright, while not can move to. So it's basically going to repeat itself until it finds a valid position to be in. Let's give this a shot. Oh, look at that. So we have a nice little wall and nobody can go there. Now, I think initially we really don't want anyone in there. I mean, I'm going to ignore the idea of doctors yet. I'm just going to move everyone out of that position. So instead of doing this can move to here, what I'm going to do is while p.x is less than 120 and p.y is less than 120. So that blocks off the entire top left rectangle. And so everyone else is being initialized somewhere else other than this small quarantine area. Okay. Kind of people. All right. Stream keeps getting frozen. Well, you may be able to play this back later on. It could be your broadband connection. I don't know. If other people are not having that same problem, then I don't know. Okay. So now, what is a hospital for? A hospital is for taking sick people in so that they are away. Well, in the pandemic situation, a hospital is for taking people that are sick out of the community and into a kind of a quarantined area where we can heal them. Okay, so we have a hospital. Now, sick people are only moved into a hospital when they are recognized as sick, you know, when we run a test. Okay, now I'm going to start off that basically as soon as somebody gets sick, they are moved to the hospital. But then after that, we'll write in this idea of tests. Okay, so run movements. Run infections. So, okay. So run infection is where we were deciding does an infection infect somebody else. Now, actually, this is not going to work. We kind of have to do this. We have to, if we immediately move somebody into the hospital as soon as they're sick, then the initial tree that we're infecting will be immediately moved to the hospital. And that means we're not really going to see anything. We're just going to see the 3 people sitting there in the hospital until they get better or die. So instead, what I'm going to do is we're going to do this test idea. Now, a test is basically what is the chance that you are being tested and found to be, yeah, what's the chance that you're going to get tested? So let's just add a test chance. So we'll create another new input. There's immunity chance, death chance. I'll just copy one of these. Test chance. ID equals test chance. Okay. Let's make it 1 in 10. So what does this test chance mean? Okay. Now I'm going to say that this test chance here is the chance, once you're sick, it's the chance that you are recognized as sick. Okay, and it's a chance per turn. Okay, and what happens when you are recognized as sick is that you are then moved to the hospital. Okay, can you move the people out once they're immune? It's an idea, we will get to that. Okay, right, so let's have a look at this now. So we're running infections. After the infections, it's running immunity. But let's put, just before that, we're going to run tests. Okay. Run tests. We'll close that one off and start the new function. Run tests. Right. Now, what we need to do now is kind of similar to the run infection. No, it's actually more similar to run immunity. It's very similar to run immunity. I'm going to literally copy this code into here. It's very similar to run immunity because we are checking for sick people, and if they are sick, we're going to check and see, do we recognize them as sick, and if so, we'll move them into the hospital. Right, var chance equals test chance. Now, if mat random is less than chance, then we're going to move them. Now, this is going to do something very strange, I think, but we'll get to that. Right, so p.x equals, let's say, math.random multiplied by 100. So put them in a random position in that block. And p.y is equal to math.random multiplied by 100. Okay. And then it goes and runs immunity. This is going to work, but it's going to look weird. Well, it might work. Oh, look. Hospital. But we still got some sick people out here. But eventually, hopefully, they're recognized before they pass this on. 1, 2. There's one sick person here. Oh, that person got immune outside before they were brought to the hospital. There you go. All right. And then one sick person left out there. This person here just hasn't been tested yet. And now they're in. Now, what does that mean? Okay. We've got all the sick people in one place. They can't infect anyone out here. Okay? So what that means is the more people that we test, the more often that we test people, the more likely we are to find somebody before they can pass it on to somebody else. All right? And then we've got, what was blue? Blue was dead. White is immune. Okay. The white, now, can you move the people out once they're immune? Yes, we can do that. Yeah. All right, let's do that. Just to be nice to them. You know, we don't always have to keep them in there. Now, you can see every now and then one of the people in here is jumping around. That's because they're still sick. P state equals 1. But we didn't say, like, and we're basically saying if you're sick, there's a random chance you'll be put into the hospital in a random position. But we didn't say if you're already in the hospital, you don't have to be put in a random position in the hospital. Doesn't really matter. Okay, so run immunity. Now, so we'll say if math.random is less than chance. So this is if you become immune. We want to know if you're in the hospital, can you be put somewhere outside the hospital? All right. If p.x is less than 100 and p.y is less than 100, then, well, we'll just put this below here. We say that p dot x, I'm going to put them in a random position from there to there because it's much easier than trying to find a random position that isn't that square. So p dot x equals math.random multiplied by SW minus 120 plus 120. There's a reason for that. I'll explain in a moment. P dot y equals math.random multiplied by SH minus 120 plus 120. I'll explain in a moment. Okay, this should do it. Let's try it out. Sick people, and they're being moved into the hospital. Okay, and has nobody become immune yet? There's an immune person, but that person was already out. Right, these sick people have not become immune yet. Let's increase the immunity chance. Oh wait, there's one. Right, immunity chance, let's increase that. So there's a 1 in 10 chance now. Where is everybody? White is so similar to green in this that I just cannot see them. Okay, let's try this again, but I'm going to increase the infection radius just to make more people sick at the same time. Reload. Alright, so people are getting sick. Oh, the immunity chance is too big. Let's bring that down. Okay, people are getting sick and they're being recognized and moved into here. Alright, the infection is spreading here. Can you move the people out once they're immune? Yeah, we're working on that. So I'm hoping to see some immune people to appear around here. I'm going to increase the immune chance now. Look at all those sick people. Okay, so I've increased it now. And they should start vanishing. Oh! I know what I did wrong. Math.random is a function. It's something you need to run. It's not a value. That's silly. Let's try this again now. So we'll change this immunity chance down to 0.01 again. Right, so people are getting sick. They're being recognized, being pulled into the hospital. And, oh, look, there's an immune person. Immune. All right, that's working. Now, just to explain this code, now, what I've done here. Now, see that the immune people are all appearing in this square here. None of them are here. None of them are here. Like some here because they were sick and they became immune naturally. Right. So what's happening here is that if we do a math.random, you get a number between 0 and 1. It's a floating point number between 0 and 1. And then we multiply that by SW, which is the width of the screen width, minus 120, which is this width here, of the width of the wall, which will give us a width from here to here, okay? So we have, the X will appear somewhere from here to here. But then we add an offset of 120 to push them out. So we're pushing them out past that wall so they reach from here to here, okay? And if we do that with the Y as well, well then that means we end up with them from here to here. So we end up with this square here. That's square. All right. So That's a lot of sick people. But all the healthy people out here are no longer getting sick. All right, what else have we got here? So, you know the way people in the hospitals have a higher chance of surviving a virus, would it be possible to lower the death chance and higher the immunity chance in a hospital? Yes, I was actually thinking of that. So, what we can do is we can add in a new, let's say a multiplier, and the chance of survival. So this immunity chance, for example. All right. In fact, it wouldn't increase the immunity chance, it would decrease the death chance. Okay? The difference is the immunity chance is the chance that you become immune to something, but that's not up to the hospitals right now. There is no vaccine, there's no way of curing this. All we can do is care for people until they become naturally immune themselves. So what we want to do is reduce the chance of dying while in the hospital. Okay, so hospital death chance multiplier or death chance divider. What would we call that? I don't know. Let's see. So we need to create a new input box, and we'll call that underneath that chance survival multiplier. Hospital survival multiplier. Yes, hospital survival multiplier. Technically we're going to be dividing, but we're going to call it a multiplier because we're multiplying the chance that you survive. It's kind of weird. All right, survival multiplier. It's not survival chance, it's survival multiplier. And the value is going to be something like, let's say it is 10. Start off with 10. Okay. Now, run deaths. It's going to be in here. So we want to find out first. Now, this is the var chance. We're finding out what is the chance of a person dying. We want to divide that by the survival multiplier if you're in the hospital. So, if p.state is equal to 1, so if you're sick, we want to say this person's chance is equal to chance, because the chance is going to be different for each person now. We're no longer using the same chance. So p chance is equal to chance. Now, we'll change this to p chance as well. If p.x is less than 100 and p.y is less than 100, then they are in the hospital. So we can say survival multiplier. We need a survival multiplier. Okay. That's very big. I don't like that. Survival mult. That's good. Okay, so p underscore chance is divided by the survival multiplier. That's simple as that. Simple as that. Let's give that a shot and see what happens. So, to see this happen, we're basically going to have to increase the death chance and then decrease. And all right, so the chance of death is now, let's say 100, 1 in 10. 1 in 10, so everyone's going to die. Right, so we can already see that all the people that were sick outside are dead. All these blues. But the people that are in the hospital are surviving. Now, I would expect some to die. Let's do it the other way around. Let's make it that if you're in the hospital, you're more likely to die. Let's just to test this. So death chance is 0, and hospital multiplier 0.01. Okay, reload. So now you should be more likely to die in the hospital. Something's wrong here. Something's wrong here. Right. Can you move the people out? You know the way. Or when there are too many people in the hospital, tests are cancelled or no one. Now, we're getting complex. What if there was a limit to the amount of people the hospital could take? That's it. We're getting complex. I want to make this work first. Okay, p.state is equal to 1. If you're sick, then var p chance is equal to chance. P chance is equal to chance, yes. If p.x is less than 100 and p.y is less than 100, so if you're in the hospital, then p underscore chance divided by equals. Let's just have a look and see what actually is that. Right. Now, oh, look at that. Not a number. All right, is that, do you know what? I probably spelled this wrong. That's probably what it is. Survival multiplier. Survival multiplier. Multiplier. There. Okay, now that's more like it. Okay, so p underscore chance is less than. Now let's bring this right down to 0.01. Oh, everyone's dead. Oh, no, I didn't want that. All right. Okay, there we go. That's a bit better. So now we can see the sick people are still surviving. They have a 10 times chance. If they go to hospital, they're 10 times more likely to survive. Okay. All right. So the key thing to take from this is that if you test, well, then you're more likely to survive. Okay? The people that are not being tested, let's say countries such as, I'm not going to pick on any countries, you know the ones I'm talking about, that are not testing appropriately. Those countries are infecting more and more people. So that means that more and more people are likely to get sick and die. If you test, well, then you will catch the people that are sick before they can infect other people. And then, care for them, make sure they have a good chance of surviving. It increases. Let's have a check of this, actually. So we've got uninfected 2 and infected 98. So we've got, I'm going to wait for this to die down. See how many people actually die or develop an immunity. Let's say we increase the chance of immunity to 1 in 10. That person, dead, right. All these people now should get healthy enough soon enough. Restart. I want to see what happens from scratch. But a few sick people here. Not being tested quick enough, so they're infecting other people. Now, you can see immunity is developing very quickly, but we still have a few deaths. Okay, we've got 8 deaths. Now, if we one sick person and only one sick person left altogether, why is that? Okay, let's see. It's because there's a 1 in 10 chance that you will be tested before you pass it on. Let's reduce that. I'm going to see what happens now if I reduce the test chance and reload. So 8 people died this time. Okay, so now we're simulating a lack of testing. Okay, so there's 10 times less testing going on. We'll see if the death goes higher than 8. 9. We're at 9 already, and we still have sick people out here. Okay. So if we increase it, sick people, so 1 in 10's chance of them being, see, recognized and taken out of their communities into the hospital. 1 person left out here. There we go. They're all inside. Now, I saw a video a couple of days ago where somebody was complaining, saying that they took a video where they were going through a hospital car park and saying, oh, there's nobody here, there's nobody here, there's obviously something going on, there's nobody here. They're inside the hospital. They're not in the car park. They're inside the hospital, okay? That's how this works. You know, you don't let sick people wander around. You have to keep them inside. And if you are taking care of the sick people, you stay inside as well. Right. So, do we have any questions so far? Why is there... Oh, long travel. Yes. There was a chance. This is a chance that somebody just took a trip and arrived in there. Okay, any questions? What if there's a limit to the amount of people the hospital could take? Do you know what? We could do that. It's slightly more complex, though, because what we're doing there is we're deciding if you're sick, we're going to now count all the people that are in the hospital and decide whether to move you or not. It's a bit more complex because you then have to go, at the way we've written this, you have to go through every person on the map and see, where are you? Are you in a hospital? Are you alive? And then decide. The system that we've written here is not the most efficient. There are more efficient ways of writing pretty much everything that I've done here. Like for instance, sickness. The way we're handling sickness is we are measuring the distance between every person and every other person in the whole system. That's a lot of calculations. How many people are there? There's like 2,400, something like that. Well, that's 2,400 multiplied by 2,400. That's doing more than 1 million checks. Let's say 4 million, something like that. 4 million checks every single time that you see anything move on that. It's 4 million checks. Do you know if it's possible to render a moving dot simulation like this in Matplotlib? I have no idea. I no idea. I don't even know what that is. I'm guessing it's a program. Don't know. I don't know. Okay, so anyway, we've got everyone's still moving around, everyone's healthy, only 15 people dead. That's pretty good. Let's bring this back down again and see what happens if we reduce the chance of testing to 1 in 100. What is the normal hold of patients allowed in a... You mean the normal number? The normal number of patients allowed in an average size hospital? You're asking me about hospital business. I really don't know. I think hospitals take sick people in. Basically, they you know, it's not like they don't turn away people. If the hospital's extremely busy, then they will move you to another hospital if they can find another hospital that isn't as busy. But all hospitals are busy at the moment. You know, so hospitals are not going to turn you away. You may end up sitting in the waiting room or lying on the ground in the waiting room, but they're not going to turn you away. Wait, I'm Googling it. Okay. What if you make each person raise a counter if you go to the hospital and lower the counter if you die or get immune while in the hospital? Good thinking. That's good thinking. Let's do that. Alright. Let's do that. So first off, before I do that, dead 8, immune 109. That's because we left the chance of immunity there. Reduced that a bit. Now that's good thinking. That's an example of optimization. Right. So we'll say there is a global variable called hospitalized. And in the init, we're going to set hospitalized to 0. And then whenever somebody's moved into it, so we'll say run tests. Okay. Hospitalized plus plus. So that adds 1 onto hospitalized. And we'll say whenever they become immune, then hospitalized minus minus. Now, there's a mistake here, and I'll explain that in just a few minutes. I want to see what happens first, and then I'll explain the mistake. So I'm just going to, at the end of show population, just before it restarts each round, I'm going to output how many people are hospitalized. In fact, why am I doing that? I could just do that in this. Oh, pop stats. Well, don't need that. Just do it here. Hospitalized, 0. Nine, 17. Okay, 27, 38. So, are there really 90 people in there? What do you think? That's a lot of people hospitalized. I mean, if you look at that. There's actually more people hospitalized than there are infected. Why is that? If there are too many dead people inside the hospital, or then you'd have to literally step on. Dudes. Oh, jeez. Right. Let's go back to this. Now, the reason that we have more than 1,000 people hospitalized, even though only 265 are infected, is because we're testing not just people that are sick and outside here, but we're also testing people that are sick and inside here. That's what's going on. So we need to ignore the people that are inside the hospital. Okay, so run tests. We don't want to run tests on people that are sick and already hospitalized. Okay, so if p.state is equal to 1 and p.x is greater than 110, greater than or equal to, and no, that's not going to work, and not p.x is less than 100 and p.y is less than 100. Okay. Now, that should be a lot more realistic. Let's reload this again and see what happens. Oh, what's going on there? Alright, yeah, okay. Right, so hospitalized, 23. Now, is that more realistic? That looks a bit more. Yeah, that looks more realistic. Right. Now, let's see. It's a library for Python that allows you to draw graphs and visual data representations. But okay, I Google, and yes, it's possible. Okay. Around 1,500 to 2,000 in average USA hospitals 2018 study. Yeah, that depends on the hospital size. A small hospital won't have that. So you're talking about different hospitals, different sizes. So, but you have to boot the dead people. If there are too many dead people, Jesus, dude. All right. Well, in this particular case, that's not happening because, as was said earlier on, these people don't have physical size. It's not a physical simulation. You can literally walk through each other. So we don't have to do that. All right. Now. Okay, so I'm going to ask for a few questions and answer them in just a minute. I'll be back in just a minute and answer your questions, right? Don't go anywhere. Yes, I'm back. Right. Ghost pandemic. Everyone are ghosts. Yes. Yes, literally. Everyone can just basically walk through each other. Okay. Right. So we have all the sick people now in the hospital. We have some dead people. Now, what would you do with those dead people? I mean, we could put them in a morgue, or there's no real need in this simulation because there's no effect from dead people. There's like you can't get sick. Now, I think what's interesting in this case is that we've got dead people outside, and if we count the number of dead people outside, 1, 2, 3, 4, 5, 6, 7, 8, 9. And count the dead people inside the hospital, 1, 2, 3, 4, 5. There are more people dead outside than there are inside. And that means, and if you think about it, right, if you think about it, we brought all the sick people into the hospital. So there should be more dead people in the hospital than outside, except that the hospitals are helping them survive long enough to become immune. Once they become immune, they're brought out again. So that's what's going on here. Now, how do you measure the real-world accuracy of this simulation? Yes, is the answer to that. That is a difficult question. Now, there are a lot of differences between what we're doing here and what is happening in the real world. I'll give you an example. All right. One example is in this simulation, when somebody passes on the sickness from one to another, that other person is immediately infectious. That is not realistic, okay? Now, realistically, what happens is somebody will get sick, the virus is inside their body, the virus starts populating itself, and then it becomes populous enough that it basically starts coming out of your body, through, liquid or whatever. So that wouldn't happen immediately, It wouldn't happen immediately. It would take like a day, 2 weeks, whatever. You don't get infectious immediately. Okay, moving the graveyard. How do you measure the real-world accuracy of this simulation? Well, you basically have to measure. Now, in the real world, we're not testing everybody because we don't have enough tests. So it's very hard to tell if the tests are accurate. I suppose the only way you can really test is by looking at the predictions of immunity and deaths. And if your predictions match, if you do a simulation, you'd have to do a load of simulations because every single one of them is random. So you have to do a load of simulations and then get the average of deaths predicted, the average of immunities predicted, and then see if that matches reality. It's not easy. It's not easy. And, when you're talking about that, you're talking about things like right. If we were to look at, I'm just going to pull up a prediction here. I'm going to pull up the reality of what's happening in Ireland. Okay, I'm just going to open up Coronavirus Ireland. Let's see. And show you something. Where's it gone? Where has it gone? Hold on. Where has it gone? There it is. Right. Okay, so this is Ireland. Now, this curve is quadratic, kind of, in nature. Now, what I mean by that is that it is possible to come up with a formula that will predict very, very closely how this curve will continue into the future. All right? So it could go straight up like that, or it could peter off like that. But the way you predict something from the future here is you try and take as many data points as possible from the past and come up with a formula. And if your formula doesn't stray very far from the points predicted on this, well, then you could say that your formula is accurate-ish. Now, it's impossible to tell. It's impossible to say that it is accurate, because you're talking about the future, and the future changes. And the future especially changes when you know what the future is. You know, if you, like for example, in a stock market, if you know that a certain company is going to raise in value, well then you might buy a load of it. You're changing the future by doing that. Viruses hijack cells and force cells to create more copies of the virus. Some types of viruses hide in the cells from the immune system. Others suppress the immune system. They don't have a nucleus. That's right. Viruses are basically just packs of proteins that, you know, they're like little programs that just kind of latch onto a system, and they, and they use the system itself as a way of reproducing itself. I mean, some people say viruses aren't alive. Technically, are they? I don't know. I mean, they kind of do reproduce. They use other systems to do the reproduction for them, but they are reproducing. In a way, we are the same. You know, we are composed of billions and billions of different cells, and each cell is dependent on all the other cells around it to do its own job of reproducing and gathering in food and energy and stuff like that. The virus, as far as I'm concerned, is the same. But I'm not a biologist. But my opinion is that if it looks alive, it might be alive. Is that why they call computer viruses viruses? Yes. A computer virus is basically a very, very small piece of code that takes advantage of an operating system to reproduce itself and go out into the world again. Okay, some viruses are kind of benign. They don't want to ruin your system. They basically want to, like, there are kinds of viruses that you find on a website, for example, where it will basically find a way into your system in order to put ads in your system. You know, it's kind of benign in a way. It's not destroying your system, you know, but it's still shouldn't be there, you know. But then they want to carry on and infect other systems similar ways. Now, there's a number of different ways of doing that, but a computer virus generally doesn't want to destroy your system. Generally, what they want to do is to use your system. But viruses in real life don't really, they don't know that. They're not intelligent. You know, they basically just want to reproduce. Now, they might reproduce so fast that they destroy the host. That's when humans die. You know, and that's a bad design in a virus. The origin, yeah, that is the origin of the name. It's the same with bugs. Actually, a computer bug is even more interesting because what is the nature of a bug? A bug is a really small insect that can get into things. The first computer bug was, I think it was a moth. I mean, I'm talking about a real, actual moth that got into a big computer and it fried a few circuits. And that's why they called it a bug. It's a computer bug. So there's a lot of different kinds of virus as well. Like there's the Trojan virus. Okay, now if you think about Greek mythology, there is this story of the Trojan horse. Okay, where some people left a big wooden horse outside Troy, and they had and the horse had a few soldiers inside it, and the people inside Troy thought, "Ooh, a present! We'll bring that in." That's the Trojan horse being pulled in because you're inviting it in. The same thing happens in Trojan viruses. Now with a Trojan virus, what's happening is that somebody sends you an email or something, and the email says, download this program and you will get whatever. You know, download this program to optimize your computer. Download this program and you'll have faster internet. And people that don't know any better do that. They're inviting it in. They're inviting the program into their computer and then they run it, and that's a virus. Most malware are classified as worms because they're independent and don't need to infect other files. They're standalone executables. Alright. I think the first virus was a worm. Yes, the first virus was back when the internet was young, 1970s, 1980s. There was no real concept of security. It wasn't really all that important, which is very strange because the internet was invented by DARPA, which is a defense system. So you could, if you knew how people's computers worked, then you could find ways of getting them to install programs. So you could actually write a small virus which would copy itself into somebody else's machine, and it would then copy itself, blah, blah, blah. Now, there's actually a very, very simple way to write a computer virus on your own machine. So you can infect your own machine. Now, I'm talking about Linux here. Let me just show you something here. I'm going to write something very simple, and I'm not going to run it because I don't want my computer to stop running. But I'm going to show you what it looks like. Okay. Hash bang bin bash. Now, what did I call this program? Let me just check that again. Vim virus.sh. So what happens if I go virus.sh? Now, that's not going to do much. Okay, that's maybe run out of RAM or something like that. If I add this little ampersand at the end of I'm writing something in a language called Bash. Okay, that's what this bit here is. And if I make that writable, then I can now run that program. If I do this, you can see if I press enter right now, I'm going to break my computer. I'm going to press delete instead. So what is this doing? Well, this just tells us what program, what language are we using. And in this case, we're using something called Bash. And Bash is basically your command line, a command line programming language, right? And in this, I'm just saying, run the program virus.sh in the background. In the background means that it's not going to wait for this to finish before going on to the next line. It's just going to run that again. So the first time I tell it run virus.sh, it then on its own is going to run 2 copies of virus.sh. That then in turn is going to run an additional 4, and that will run another 8, run another 16. This is exponential. It's a virus. It's going to run as many copies of itself as the computer will let it run. And computers are stupid, so the computer is not going to stop it from running. That will ruin your computer. Don't do it. Today with Kay, how to make money but get caught in the process. Yes. They called it a bug because at a showcase for a new computer, big computer, like room size, it didn't work. The mechanics found a moth in one of the glass shells. Right. Right, sudo rm. I don't think so. I'm not that silly. I know these things. Okay, yes. All right. What Alistair, I got your name right this time. What Alistair is saying is this sudo rm minus rf no preserve root slash. What will that do? That will delete everything on your computer, including itself, including all the programs, the operating system, everything. Do not do that, and never do it to somebody else either. I'll give you a little story here. Back in the 90s, there's a friend of mine whose brother, his computer was running out of space. Hard drives were very small back then, like 100 meg was a lot. I remember spending £150 on a hard drive that was 100 meg in size. It was big. There was a lot. But you still run out of space if you're recording things like music and all that very, very quickly. So this guy was running out of space. So he just went on his computer looking around and trying to find things that he could delete in order to make more space. And he found one and he thought, I don't know what that is, and it's taking up a lot of space, I'll just delete it. And so he deleted the C drive /win directory, which is the Windows operating system. Bye-bye. That killed that. Okay, so yes, viruses are easy enough to write if you have access to the machines. Okay, so the goal of most security systems is to stop that from happening. It's to stop people from just having unauthorized access to machines to do that. So, for example, Outlook used to allow you to run VBScript within emails. So you could send an email to somebody that contained programs, and the programs would actually run. And, you know, the hair's raising on my head even just thinking about that. You know, that is such a bad idea and they should know better. But they did it anyway. And it wasn't until years later that they just stopped doing that and stopped allowing it. Problem with VBScript. Biggest problem with VBScript versus JavaScript. VBScript is Microsoft's version of JavaScript. They had, JavaScript was just taking off and Microsoft wanted a version of a language that could run inside things like web browsers. So they came up with VBScript, which is based on their Visual Basic. Now, the biggest problem with VBScript from a security perspective is that VBScript can interact with other parts of your system if you're running Windows. Yeah. JavaScript doesn't let you do that. You can't use JavaScript and say, oh, can you run this program? It doesn't. It won't do that. It's sandboxed. Okay. With a new tool called virus.exe. Yeah. Any questions? Let's get back to this topic, actually. Have we got any questions about this pandemic simulation? Yeah, I think that's interesting. Okay, yeah. So we're basically, this simulation, I think, just kind of, it kind of hammers home the point that testing is important. You know, and that if you think you're sick, even if you don't have a test, then you need to isolate yourself. Because if you don't, then you will make other people sick. And it's best not to do that. Will there be a part 3? Probably not, because I'm running out of things to do here. I'll tell you what though, I think in the next class, I'm just after getting the domain name Monaghan CoderDojo.ie. So in the next class, what we're going to do is create that website. I don't think we can continue on this pandemic any further because we kind of got to the end of any useful things we can do here without doing big rewrites. Now you could, we talked in the last time about doing countries and things like that. You saw the work that goes into just creating walls. All right, now country is like little areas that have kind of curved walls, weird walls around it. It's not as easy as it might be. There better be. What would you do in a third one? What would you do? To model the spread of malware, yes. Yes, you could. Yes, you could do that with this. Yes. In which case you would need to change how the map works. If you were to model the a virus network, computer network, well then you're no longer talking about a two-dimensional map, which is what we have at the moment. A two-dimensional map is basically you have x, y coordinates, but that's not how computers work. Computers work on a node basis, right? So you have a computer which is connected to a number of other computers. So it's actually more like a web. It's like a World Wide Web, where you have one node which is connected to other nodes via strings. Let's fill up the website with Trojans. That's not. I'm thinking, like, what would we do with a new website? So what I'm thinking that we need to have one piece which you lot don't have control of, which will be the front page. Okay, that'll be the WordPress page. But I also think that you lot should have control of some parts to, you know, do your own little things. What would you like to do on a website other than Trojans? I wonder what the lag is in this. I mean, is it 10 seconds, 15 seconds? All right. In fact, it must be less than 60 seconds because it's currently 13:31 here, and I see 13:31 in that video I'm looking at. I'm not seeing any suggestions yet on that. Okay. If we were to model a computer network and viruses, we'd need to change how the map works, so we're using nodes instead. Now that's a lot more complex. We could get a start on that if that's interesting. Let's fill up the website with Trojans. I want to give it a virus. Same thing. Now, do we find that interesting, I wonder? I use my website as a file cloud server. You could store all the projects we create on the website. Yes, we could do that. Now, I would have to, I'd have to restrict how much everyone has because, you know, with the best will in the world, there are people that will just upload movies and things like that. You know, that's not what it's for, you know, but yeah, like, yeah, if you need to do things like store a number of images for your project or a small video or something like that, yeah, fine, that's great. But we are going to put restrictions on how much space you can use in your things. You could store all the projects we create on the website. Yes, absolutely. I'm going to be doing that. And I think every time we do anything, we should write up a blog post just explaining it. I think we probably need a forum on it so people can ask questions. And I think people need, you need your own subdomains. You know, so you could have, for example, well, you're not getting gangsterjfyt.monaghanCoderDojo.com. But you might get, let's say, evan.monaghanCoderDojo.ie or Alistair. You know, you'll get your own domain names that you can do whatever you want with it. Now, I can give you templates that you'll create your own website and then mess around with it and break it if you want, and maybe I'll help fix them after you break them, maybe. All right. Anyway, all right. I think I'm going to get started on the website during the next 2 weeks. But for the next class, I think that idea of a computer network kind of simulation is interesting. And we might do that. We might do that. Okay. Any further questions? You know, I wish I could just draw what's in my head. I wish I could just okay, and now you see it all. Because in my head, I'm just thinking of this kind of growing network thing, and it just things kind of expand out so you can see everything. And if you add a node, it just kind of pops into place and things pop out, and then you can see it grow. All right. Okay, I think we're at the end of this. Right. I don't. What did we add in this? We added the hospital. Should use the Nextcloud system for the file storage. It's good. I'll look that up. I don't know what that is. There's Dropbox, Nextcloud. I don't know. But like there'll be enough space. There'll be enough space for people. It really depends on what you want to do. Now, most simple projects would be things like HTML, a couple of MP3s, really, really simple stuff. So you're not really going to need a lot of space. I'm going to start off by not restricting anyone. Just do what you want. But the moment I see somebody doing something mad, I'm going to step in and just stop doing that, please. Right, so we'll do that from next class. Right, this class, I think we're done. We have created a small quarantine area. We have shown that moving all the sick people into that quarantine area, it really, really helps. You know, look at all these healthy people out here. It really helps. And we've shown that when you do a lot of testing, you know, you're basically stopping the pandemic from growing. You host it yourself in your own server, not like Dropbox. Well, then what's the point? I mean, why would you have a storage system on a computer which already has storage? Why not just use the computer? I don't know. I'll look it up. It could be that maybe it's a few different machines hooked together into some sort of cloud storage thing. If so, that's interesting, and I'm going to look into it myself. Personally, for cloud storage, I use something called Spaces from DigitalOcean. They have this thing called Spaces. I'll look into that. Anyway, I'm going to call this a day. It's a little bit shorter than last time, I suppose. But next time, I think we might actually do that computer node idea. So we'll talk about that. Okay. See you all later. Now, how do I shut this down again? There it is. Yeah. Bye.